So welcome back, everybody. So we were looking at this, and I was asking who of you sees a tree in there? Who sees a tree? So it seems to be a bit half-half. So some of you actually see it, and some others do not actually see it. So the idea is that we can draw the tree together. The idea is that that's an object, right? You agree this is an object. So we can put this object or a proxy for that object as a node in the tree. How many keys does that object have? You can directly say it. 2, yes. 2 keys, foo and bar. Foo is associated with the value true. That's an atomic value. And bar is associated with an array. You recognize the square brackets, right? And in that array, how many elements do we have? 2, yes, indeed. The first element is an object, and the second element is a null, right? So you see in these yellow rectangles, I'm putting the atomic values, so strings, nulls, booleans, and numbers. I'm putting the objects in purple and the arrays in red, right? So now my object, how many keys does it have? 1, foo bar, foo. So this is a tree, you agree, right? So, of course, biologists don't see trees in the same way. Mathematicians don't see trees in the same way. The difference between mathematicians and computer scientists is that for a mathematician, a tree doesn't have a root. It's just some subgraph that doesn't have any, some graph that doesn't have any cycles, undirected. But computer scientists consider that it's a rooted tree, right? So we just say tree, but it's a rooted tree. So it means that we do have a root here, and that's directed arrows that go to the children. So this is a tree structure. Now, a comment, the keys here are not nodes. These are just labels on the edges. This is a node. All the rectangles are my nodes, right? And these little circles here, ellipses, are basically just labeling the arrows that come from an object to one of its value, right? Every time you have an object, you label the arrows that come from here to here. For whom is that clear? Who is able to do it for any JSON value I give you? You can draw the tree. Okay. You'll have exercises, but that should be easy. Once you've done it once or twice, it's something that becomes very intuitive. But of course, the goal is not that you draw them. The goal is that if I show you that, the thing on the left, you immediately see the tree in your mind, right? So let me ask this question carefully. Who answered, no, I don't see the tree previously, but now sees it? Okay, so I have a good conversion rate. So that's my goal. I want you to see a tree. Now, this is another example. And now I did the same slide that I had with CSV and a table. Now I have it with JSON and a table. Now you have a JSON document here, a JSON object. You'll see later why I call that document, but JSON object. And that corresponds to the tree above. So every time you see the syntax of JSON, you should see in your head the tree. Now, let me introduce 2 verbs that are related to this ecosystem. These verbs are parse and serialize. Probably you already heard them, but this is basically what you call the 2 directions. Basically, what happens is that you have this sitting somewhere on your drive on HDFS S3 or whatever. What you have is a library, a JSON library or an XML library. And what it does is that it uses some grammar, context-free grammar tool that is able to parse that, and then it builds this in memory. It means that what you see here is actually the in-memory representation that is actually built in the RAM when you parse this. These are memory pointers that you have here, and these are, for example, Java objects that are basically going to be here. This is really what you have in memory. So the idea, the very important lesson is that even though on disk you have JSON or XML, you don't have JSON or XML in memory as text, you have then as the tree representation. This is absolutely fundamental to understand, right? Syntax is only syntax. So this is called parsing, and this is called serializing. when you have the memory representation, you might, for example, modify it or have some interaction with it and so on. When you write it down to this, it is called serializing. So parsing, serializing. Okay? And a misconception, this is something that people have on XML, is that XML is verbose and so it's inefficient. No, because you never process the XML text directly. You first parse it into memory as a tree, and then you work on the tree in memory. Okay, so parsing, serializing. Now this is XML, right? So this would be some XML document. And you can see, if you see the correspondence between the two, you have the element A right here that corresponds to this, that has D and C as children. D has an attribute that I put like this here in red. Then C has this, that's text. Then there is an element B. And then there is the dot. And the element B has itself text inside, right? And then in XML, what we do is we add an extra root node that's called the document node. We'll come back to that. Who sees that this, when you parse it to memory, you get that tree? Who sees that? Okay. And so again, the other side is serializing. Now, do you see that I don't care if it's XML or JSON? That's the same thing. We just have syntax that gets parsed into memory as a tree. Right. And the considerations for using the one or the other are based on the use case, but this is really the one and same thing. Right. Okay. There is a bit of a difference in the paradigm between the two, and that I try to regularly make the comparison, is that when you have these JSON in-memory representations, the object keys are on the edges, on the arrows, right there. But in XML, they are not on the edges. They are on the nodes, on the vertices. In other terms, in other words, an element node, we'll see that this is an element node, knows how it's called. So this node knows that it's called foo, right? This one knows that it's called bar. However, this atomic value here does not know that it's called bar. Bar is really just in the relationship between the two. But imagine that this is the number 42 here. 42 is just 42, right? It doesn't know that it's called bar by somebody and somebody else might call it foo bar, but this is just the number 42 and it doesn't have its name right there. For whom is that clear? So labels on the edges for JSON, labels on the nodes for XML. This is one of the differences in the models. Okay.
There is a question.
Yes.
So could you go back a slide, please? So why should the object not know the edge label? I mean, I think it's just as arbitrary as knowing its parent, right?
Both are okay. Both are okay. It's just that traditionally in JSON, we tend to look at it like this. With it's kind of you could almost call it a cultural thing with the JSON ecosystem, that the model has the labels on the edges, and on XML it has the models on the nodes. You could, of course, if you wanted, you could imagine a model in JSON that puts the labels on the nodes. It's just that you wouldn't be in a majority. Basically, most of the people would put them on the edges. Likewise, in XML, you could come up with a model that also puts the labels on the edges, but again, you wouldn't be in a majority.
Yeah, I meant something slightly different.
Oh, sorry.
So you said in JSON, the nodes don't know their parents because the labels are on the edges. But I mean, in this kind of intuition, why should you not know the edge label?
So let me explain that more precisely. I'm already getting into details here. So the idea is, when you define a model, this one or this one, you basically say what nodes you have. So here, for example, you have object nodes, you have number nodes, and so on. In XML, you have element nodes, you have text nodes, and so on. The next thing you do when you define these nodes is that you say what properties they have. It's a property. For example, a property of that node is that its name is foo, right? Here, a property of that node might be that it's an object, right? But bar is a property of the edge. It's not a property of the node here. So formally, it's a property of the edge. The other thing that you define, and now I'm coming to what I mean when I say doesn't know, it's called an accessor. An accessor is like a formal API. It's a mathematical API. It's not, you cannot call it with a computer. It's just a mathematical function. an accessor, for example, you have an accessor here on an element node that returns the name of that element. So the reason I'm saying that this node knows how it's called is because it has an accessor that is able to, given that you have this stored in a variable, you can access using the accessor the name. What happens here in these JSON models is that if you have this in your hands, like this is what you have, you don't have any way of going backwards because this is an arrow that points here. When you're here, you don't have any way of accessing any property of or accessor that would bring you back here, right? In fact, these values here, the atomic values, they don't have any physical identity. 42 is just 42. You might have 42 here and 42 here. It's meant logically, but there is no notion of physical identity in there. It's already advanced what I'm telling you, but does it make sense?
Yeah, thanks.
Yeah. Oh yes, here you are. Yeah, that's the idea. So it's really based, whenever you have a model, in fact, that's the basic of when you design a query language, you have to be very clean about it. The first thing you do when you design a query language is you define your data model. In that case, what are your nodes? How are they connected to each other? What are the properties of the nodes? What are the accessor of the nodes? And one of the things the accessor can give you is the children. For example, you could have here on that object an accessor that takes one argument, the name of the key, and you can call that accessor with foo, and it's going to return this, right? That's again like a mathematical API that allows you to navigate the model. That is the first layer on top of which you can then build very powerful query language, functional and declarative. Okay? Yes?
So you also, on the JSON side, you have oriented edges, and on XML side, they are not oriented. Is that like for a part?
Oh, no, I should add it. It should be oriented. It should be oriented in both directions. Let me be more precise. This is a very good question. So in XML, when you are here, you have an accessor that's called children, right? And the children accessor gives you the list of all the children. So this one, and so on. So knowing that node with the accessor, you can go here and you can go here. In XML, you also have a parent accessor. So it means that when you are here, if you invoke the parent accessor, you can go back here. It's very common. So that's probably what I had in mind when I didn't put the arrow in here, is that this is bidirectional, typically in XML. You can go up and down. In JSON, typically, you only go down, but there is no concept of getting back up. I'm not saying everybody would do it. You could always invent models or systems in which you add the notion of a parent. The problem is that basically you have to give you the intuition behind this. When you introduce the concept of a parent, you have to deal with physical identity. You don't have to do it if you don't have the concept of a parent. For example, if you have 42, that's just a number. If you have the concept of the parent of 42, then that depends which 42 you're referring to. It might be 3 times in the document, and each one of these 3 uses of 42 has a parent. But then you have to distinguish between the 3, right? Whereas if you don't need to worry about the parents, you just have 42, and 42 is 42, right? You can even reuse it. So there's no notion of physical identity anymore. And what I'm saying is that having a parent accessor and having to deal with the physical identity of the nodes added a cost in terms of performance and in terms of code that you need to run. It's basically slowing things down and taking more memory footprints. Does that make sense?
Yes, and maybe could you like give an example where you might need this notion of physical identity?
Yes, so that's already advanced. So don't worry, I'm going to answer, but don't worry if it's not entirely clear. We will also come back to it when we study JSONic. Imagine that you're already like a few weeks in the future and you start manipulating these trees. So for example, you might have a tree like this, and then you take that object right here, and you want to copy it over and attach it to some other object. That's part of the query you're writing. So you basically take that object and put it in another tree below another object. if you don't have to deal with the parent access or anything like that, you can use the same physical object in memory. You don't even need to clone it or anything. You just have the both parents point to the same one, and it doesn't matter. You won't see the difference because your model doesn't have the concept of parents. So you will not see the difference by not cloning them. However, if your model does require that you can go back and up in the JSON tree, and you want the ability to go back up, that forces you to do a clone of when you do it. You basically would need to take that object, clone it, copy it over. It has a performance penalty for that. And then it's the clone that you attach. Then this one, when you say parents, will return this. And the clone, when you say parents, will return something else. But there is a cost because it takes more memory. You need to clone it, and you need to keep track of the physical identity. Does it make sense?
Yeah, yes, thank you.
Yeah, awesome. That's already a very advanced question. This is really, as soon as you start designing query languages, you have to consider this sort of things, right?
A question on XML. Is there anything that XML attributes can do that XML children can't? It seems like with the nesting ability, the ability to have duplicate tags, all of these things, like having children seems to be a pretty complete solution. So I'm kind of unsure what attributes, what role they serve.
Mm-hmm. So I told you 2 weeks ago that if you want to troll an internet forum, ask the question, is JSON simpler than XML? And then look at the heated discussion that follows. There is a second way to troll an internet forum. Ask if you should use attributes over elements, and that you also guaranteed get a discussion. So the idea is that you could consider that the model is a bit redundant in the sense that you have a choice, you have a design alternative when you have to put your data in there, and there is no right and wrong, right? You could decide to put the data in an element or a field in an element, or you could decide to put the field in an attribute. So there is a bit of redundancy and redundant design. But there are cases in which you don't have a choice. And when you have nested data, then you have to use an element, because in an attribute, you cannot nest anything. The attribute value has to be atomic, right? So you see how I'm using this term atomic a lot, right? This notion of atomicity. The atomicity here is the leaves of the tree. It's basically all the values that don't have any children are the atomic values. Does it answer your question?
Yeah, I guess it seems like attributes can do, like they can have the, like, turn a tag into a map essentially where all the values are
absolutely
atomic.
Absolutely.
But I'm kind of unsure why why this is necessary as a language feature. If you're able to have, say, duplicate tags and deep nesting, is it beneficial to force that you have unique keys, have a one-to-one mapping, and not have nesting in the attributes?
There are multiple ways to interpret that. So one way is, why don't we have nesting in the attributes? Is it what you mean?
I guess what I'm saying is, why do we have attributes at all if nesting covers a superset of the attribute features?
You want to get rid of the attributes.
Yeah.
This is what you want. You could, absolutely. You could get rid of the attributes, and then you could basically put everything in the elements. What you would lose then, if I'm thinking about the consequences, you wouldn't have any built-in check that you can't have multiple times the same field. Because you might remember that elements can repeat. So you can have multiple time elements with the same name together. It's very common in XML. But attributes cannot be redundant. Attribute names cannot be redundant. So you would lose this check, basically, if you do that. This is one thing that would happen. But in principle, I mean, you could get rid of attributes. In fact, there are people that tried to simplify XML. You know, XML is already a simplification of HTML, which was even more complicated. And there are people who try to simplify XML by dropping all sorts of things that we think we don't need. There are suggestions. I think one of them is called Simple XML, I think, that is out there. The one thing that is in the way is the universal acceptance. The problem is that none of these proposals manage to get universal acceptance. So there are multiple out there, none of them convinced everybody. And here you see that one of the benefits of using XML or JSON is not so much because it's perfectly designed, because they are not perfectly designed. It is because it is universally accepted. There is one JSON standard, there's one XML standard, and you have thousands of parser libraries out there that everybody's using. You can write down an XML file, everybody in the world can read it. You can write down a JSON file, everybody in the world can read it. Now, if you require a simple, imagine you design a tool and you require a simple XML documents. Now the people who want to send you documents, they're gonna have a problem with interoperability, because then it's a substandard. It's basically a subset of XML that is not a universal standard. And then you get into this trouble that you don't have that many libraries out there that do it. So I'm kind of half answering your question, but basically the take-home message is neither XML nor JSON are perfect or perfectly designed, and that's okay, because the real top benefit we get is the fact that there are standards and there's libraries. Does it make sense?
Yep.
Okay, thank you. But it's a good question. It's good to have critical thinking. All right, so XML, JSON. Any more questions on Zoom? Okay, but this is great because we got in the depth already at that point where it was supposed to only be an introduction, but we've already gotten far in terms of these things. Okay. So now let me dive into the XML information set. What is it? It is a standard for the memory representation of XML called the XML information set. So the idea, it's about drawing the tree. We take a document right here, for example, that is an XML document. It parses, right? It is well formed, so you can parse it. And the idea is that we need to define the nodes. I told you that whenever we define the data model, we need to define what are the possible nodes you can have in there and what are the properties and accessors, right? This is exactly what the XML information set is doing. It's telling you what kinds of nodes you have. Turns out that you have 11 of them, but I'm not going to bore you with all 11 of them because some of them could be considered a bit deprecated or obsolete in their use. So I'm just going to focus on 4 of them, and you will see it's easy because it maps to the syntax we've learned. So the 4 I'm going to focus on are document nodes, element nodes, attribute nodes, and character nodes. Well, they don't call them nodes, they say information item because it sounds fancier. So this is document information item, element information item, attribute information item, and so on. But basically, these are the kinds of nodes you have, right? I'll focus on these 4. So first, that's the document node. And these here are properties. There is the children property, there is the version property, and there's many of them, but I'm just showing to you the most important ones, right? And then I'm just visually drawing it like doc here, and that's a document information item. So the first property is the children, and it has one child that is an element information item, that's metadata. That's this here, okay? And the version is 1.0, which is taken from here. And then on top of this, but I'm not showing to you, when you have a query language, you have accessors on top of that, which is get the children, get the version, and so on. These are the accessors. All right, so this is the document information item. Then you have elements information item. The properties are a bit different. There's more than that. I'm just showing you 4 of them. So one of the properties of the element information item is the local name is metadata, right? I didn't want to confuse you with namespaces, so I kept namespaces out of there. So local name is metadata. The children, 2 of them, title and publisher. These are the 2 elements that are in here. Attributes, there's none. And parent is the document information item. I told you can navigate back, right? So you can go all the way up. So the parent property is the document information item. Who agrees? Right? Okay. I'm simplifying a bit, but this is to give you the spirit. Then we have another one that's title, same properties, but now the local name is title. The children, there's just some text in title. The attributes, there's 2 of them, language English and year 2022. And the parent is metadata, right? It's this bidirectional navigation that you can go up or down to one or the other. Then we have publisher, the local name is publisher, the children, that's just ETH Zurich. You can just see it in the syntax. Attributes, I don't see anything. And the parent is metadata, right? So they have the same parents, right? Then we have an attribute information item. So for year 2022, should correct that. So the local name is year. Normalized value is 2022. Why normalized? Because you typically trim the spaces. If you have spaces at the beginning or at the end, you trim them. So that sort of thing. So this is why you normalize the value of the attributes, right? Get rid of the extra spaces. And the parents, it's called owner element, but it's really the parents, is the element information item title, because that attribute is inside the title elements. Then we have language EN, which the local name is language, the normalized value is EN, and owner element is title. Then we have the text information item, systems group. The characters is just a string. It's a sequence of bytes, sequence of characters. So S, Y, S, T, E, M, S, space, and so on, right? I said bytes, I shouldn't say bytes. I should say Unicode code points or characters. And then the owner element is title, okay? And the same for ETH Zurich, which has these characters and these owner elements. For whom is this clear, right? You can see them as Java classes, basically all of these kinds, and then these are actual objects that instantiate the classes, right? And the properties would be fields of the class. But the cool thing is that once you have done that, you can use the parents, owner element, and children properties to draw a tree. And the edges of the tree basically correspond to children and parent and owner element. Who sees that? Okay. So what we've done is we've just done some formal definition of the kinds of nodes you can have and the properties you can have, which gives us an in-memory representation that looks like this once we have parsed the documents. So this is called XML information set or XML info set for those who are familiar, and that's also a specification of the W3C. All right. What I'm telling you, I mean, here I'm showing you with XML, the principles are general. The idea that you define the kinds of nodes in your tree, the properties they have, the accessors they have, and that you can draw a tree, this is universal. This is true for XML, for JSON, for YAML. You can do as an exercise, take a YAML document and draw a tree. Try to come up with the kinds of nodes and the properties they have for YAML, for example. You might notice you're going to end up with the same thing as JSON. You can use the same model for JSON and YAML, kind of. There might be minor differences, but they're almost the same. Okay. So that closes the part on drawing trees and realizing that XML documents and JSON documents are in fact trees, and we can formally define how these trees look like in memory. And that means that whenever you start reading an XML or JSON document, the first thing you're going to do is parse it into memory into a tree. Everything else will be done in the memory on that tree. You forget about the syntax at that point. You don't care anymore about the syntax. Okay. The next step that we can do once we have it in memory is called validation. Validation, not to be confused with its sibling called well-formedness. Exactly. Do not confuse the two. Well-formedness is the first step. Well-formedness is basically a yes-no question that says, can I parse it and build a tree? If it's well-formed, yes, I can parse it and build a tree. If it's not well-formed, you will not be able to build a tree. The parser will fail. It will tell you there's a syntax error somewhere. It will refuse to build the tree. So well-formedness is the requirement for being able to build the tree. Then we have a second step. Once we have built the tree, after that, that's called validation. So you see it's a two-level. Yes, no, is it well-formed? And if it is well-formed, yes, no, is it valid? But I need to explain, of course, what valid means. Valid has to do with the structure of the document. In fact, I kind of told you about it when I introduced the namespaces, right? Remember HTML, XHTML, MathML, and so on. I told you there are constraints on the structure. Well, this is kind of what validation means. You want to validate that this is validates HTML or this is valid MathML. It means the structure is actually correct. All right, so if you use XML, it changes in every version. But the colors of the buttons are just like in Matrix, right? You have the choice between the red one and the blue one. So the blue one gives you well-formedness. Do you know Matrix? Or am I too old? You know Matrix, okay. So validity on the left, the red one, and well-formedness, the blue one. Even if it's at some other places, they usually stick to that code. So oxygen tells you if it's well-formed and if it's valid. Now, what validation does, we will go into the details of that, is it tells you if the document that you already made a tree of in memory respects a specific structure. So there are constraints that that element is only allowed to have this and that child. This object must have a key that is called age, and that must be a number, that sort of thing. This is a constraint on the structure. So in the very narrow sense of validation, validation is a yes-no answer that tells you, yes, that document checks all the boxes of the constraints that you imposed on it. It is valid, or no, it is not valid. The other thing that you can do when you validate, and typically is done at the same time, is called annotation. Annotation means you take the tree that you've just built when you parsed your well-formed document, you built a tree. Annotating the tree means you modify the tree and build another tree, or you modify it in place, it's the same. For example, you might have a text node that says 42, right? That's a text, characters 4 and 2. You might have your validation constraint that says that text node must be a literal that represents a number. It means it will accept 4 and 2 because that's a number, 42, but it will not accept foo, F-O-O, because that's not a number. And what you typically do when you have a constraint that says it must be a number is that in your tree, you actually make it a number. It means that instead of the text node 42, you replace that text node with another node that is basically typed. And here you have an integer. So it means that in your memory, instead of having a string with the character 4 and the character 2, you replace that, for example, with a 64-bit integer, and that's an actual integer. Why is that good? Because then you can use arithmetics and all kinds of things on it, and it is already in a number representation in memory. That is called annotation. Annotation means that you modify your tree so that now you have typed value because you validated that the values correspond to specific types, and then you can annotate that tree with the types. For whom does that make sense? Right? Okay. So validation in the narrow sense is a yes, no, and annotation means you slightly modify the tree to add all the types that you have resolved. Some people might use the word validation in a broader sense to include annotation. So they basically validate a document, but they also annotate it at the same time. So this is why it depends on the context, what you mean with validation. Could include annotation. Okay, so now I'm on the high level now. I will get into the details of the languages that allow you to validate, maybe not today, but next week. But what I would like to say is that what you validate might be JSON objects or XML documents that are part of a collection. You might have a collection with 1 million JSON objects, 1 per line, for example. That's a collection of objects. Or you might have a collection with 1 million XML documents. So typically, when you validate a document, you actually don't validate just a document. You validate millions of documents with the same constraints. That means that if you don't have any validation, so I'm hiding this thing in there. If you don't have any validation, your collection of JSON documents could be very heterogeneous. It could be even a huge mess, right? You could have all kinds of documents that don't even look alike, and that's totally fine. You can absolutely have that. If you bring validation into the picture, that basically ensures that all of your documents in your collection have the same structure. For example, if these documents represent people, you might want that every person has a first name, a last name, an age, and so on and so on. Then you validate that. And if all of the objects in your collection follow that are valid against the same constraints, the same schema, you basically have a homogeneous collection. For whom does that make sense? All right. So if you don't validate, the collection can be heterogeneous. The moment you validate all the objects with the same constraints, you get an homogeneous collection. It could fail. It could also tell you, no, that collection is really heterogeneous and we cannot validate it because the validation fails, and then you just stay with that, right? And that's actually fine, because in some cases, you actually do want to use the heterogeneous collection and deal with it. For example, your heterogeneous collection might be the logs that a company accumulated over 20 years, right? And they might not be valid, or because it evolved over time. So it might not all look alike. And maybe in some cases, you still want to be able to look at it and query it, even if it's not homogeneous, right? But the real nice thing, if you manage to validate that and build a homogeneous collection like this, you get a lot of very nice performance perks. Because the moment you manage to validate it, you can use even more efficient memory structures than the trees. And so that I will talk a little bit about. But suddenly, the moment you've done that, when you deal with that, everything suddenly becomes faster, right? So this is the idea. This is a bit slower, and this can become much, much faster because of the regular structures that you have in there. And in big data, we have everything. We like it if it's heterogeneous. We like it if it's homogeneous. We just associate it with performance. If it's homogeneous, just comes with better performance because you can store it more efficiently in memory. Okay, so that's an example of documents that would be difficult to validate or to create a schema. Why am I saying that? Because you see in this array here, there's a bit of everything. You have a string, you have a Boolean, you have a null, you have an object. So if you would like to specify what kind of type it is, you would say it's an array of whatever. But you cannot say really an array of what. It's not an array of strings, it's not an array of Booleans, but this is fine, right? But it's just that this has less structure. Here too, you have an integer, and an array. So it's not an array of integers. It's also not an array of arrays of integers. It's just an array of whatever, right? So this is the idea here. So this would basically be absolutely okay. JSON allows that, and you might actually have data that looks like that, but it might not be super fast to process with this heterogeneity. This, on the other hand, this is the intuition I want to give you, has a bit more structure. How do I see that it has more structure? Well, here I can see that I have an array and I have 3 objects in my array. It's already a good start. These are only objects, so it's an array of objects. But if I look inside the object, I also see that these objects all have a key foo associated with always a string and a key bar that turns out to be optional. It's not always there, but it's always associated with an array of integers. Do you see that here? It's something where I can very naturally define a schema saying it's an object. A is an integer, B is a Boolean, C is an array of objects, of which a required key is foo associated with a string, and an optional key bar is associated with an array of integers. For whom does that make sense? What I've just described to you is called a schema. A schema would tell you exactly that structure. And then you can validate against a schema. So far, so good? Everybody's following? So
There is one question.
yeah.
So can you define a schema for a heterogeneous array where you say it's exactly this length and the first element is of this type, maybe the first element is a string, the second one is Boolean, et cetera, or?
Yes. But I have to explain a little bit. In fact, it's a great way to use the last 5 minutes because then I don't have to open the next part. So the first thing that I will say is that there are multiple schema technologies. They compete with each other. We'll look into a few of them. JSON schema is one, XML schema, but there's also relaxing or relax-ng, I never know how it's pronounced. So there's alternate technologies. So there's different schema technologies. These technologies do not necessarily have the same features. They might be a bit different. Some technologies will allow you to do things that other technologies will not allow you. However, in the context of XML and JSON, most of these technologies have sufficient flexibility to allow you to still manage to validate something like this in 2 ways. The first way is when I said what is the type of B, I said a bit casually, it's an array of whatever, right? An array of whatever. But in fact, most schema technologies allow you to say it's an array of whatever. You're allowed to say that. And then it will validate that successfully as an array of whatever. And that's totally fine. So this is the first answer to the question. And here too, you could say it's an array of whatever, and that's it. But of course, the consequence is that if you have a string with a number in there, it will not annotate it because you just say whatever. So okay, whatever, I'm just leaving it as it is, right? But if you said it's an array of integers, then it would be able to also recognize the integers and store them. So that's the difference. So that's the first part of the answer to your question. Most schema technologies allow you to say things like an array of whatever without further specifying or constraining the contents. The second reason why you can do it is that many schema technologies also allow you to write code describing the constraints. It means that you could say not only B is an array of whatever, but you could write actual code that says the first one is a string, the second one is a Boolean, the third one is a null, the fourth one is an object with foo associated with a string and nothing else. The thing is, you would have to write it yourself. It's an extra piece of code that the user have to write, and many schema technologies allow you to do that. It's kind of a user-defined or generic constraint. It's less convenient, of course, than all the constraints that are much like saying this is an integer is much easier, but you can do it, right? So in these two ways, you can say an array of whatever, and you can also provide some computer code that describes more precisely exactly what you want. Then it's Turing complete, basically. Okay.
Thank you.
We also have more time for a question. Yeah. Maybe the last one, then I have to let you go.
So you mentioned about the performance, that when we have like a schema, it will improve the performance. But intuitively speaking, like when you have the validation, you have to add the validation for every time you write it. So in terms of like inserting more, you will have to have an additional step. So how would that compare? Because it will add some overhead of checking.
Yeah. So this is an excellent question. And again, this is anticipating on some things we will see later. Indeed, we will see that the behavior of validation is different from the behavior you have in a traditional relational database. In a traditional relational database like PostgreSQL, you have to validate the data. You don't have any choice. The first thing you need to do is create table. You have to specify the columns and the types. So you have a schema, you have to do it. In the case of big data in XML and JSON, you're not obliged to. You can also have a collection without any schema. You can add the schema later. Like a week later, you can come with a schema and say, from now on, I would like to enforce that schema. You are absolutely correct that from the moment you add a schema that enforces a penalty when you write new data, because it has to validate that data. It becomes slower when you write, but it becomes faster when you read it again. It's always a compromise. There's no free lunch. It's like time and space or algorithmic complexity. That's the general idea. But I'll come back on that many times because you already opened a very interesting topic in there with your question. Okay. So that brings us to the end of this hour. Tomorrow, I'll talk about types and the type system of schema technologies. Until then, have a nice evening and see you tomorrow. Thank you.